Hi, Assalamualaikum warahmatullahi wabarakatuh. This session we are going to learn another physics topic, which is wave optics, interference and diffraction. So in this session you're going to learn about superposition and interference, Young's two-slit experiment, interference in a reflected wave, diffraction and diffraction gratings. So at the end of the lesson, you're going to be able to obtain this learning outcome. You may refer it to the lecture notes that has been given earlier. So we proceed with the lecture. The first topic, superposition and interference. Interference is only noticeable if the light sources are monochromatic and coherent. Monochromatic means different light sources have the same wavelength, and coherent, different light sources maintain the same phase. And then interference will be constructive or destructive. Constructive where two waves are in phase, and destructive where two waves are out of phase. So this is the example. Two waves may interfere either constructively or destructively. Okay, the two waves the first one and the second one has the same wavelength, and they also have the same phase, meaning that they have the peak at the same time. Okay, let's say the peak, the maximum at the same time, and then the minimum at the same time, so that we can say both of them are in phase. Okay, and then of course they have the same wavelength. Okay, this is the first peak of the first wavelength, the second peak similar to the first peak and the second peak of the second wavelength. So constructive interference will occur. And then another example is for the destructive interference, where they have the same wavelength but they are out of phase. So destructive interference will occur. So interference will be constructive if the path length differ by an integral number of wavelength, and interference will be destructive if the path length differ by a half-odd integral number of wavelength. To summarize, the two path lengths and will interfere constructively or destructively according to the following condition: L2 minus L1, or length 2 minus length 1, equals to m lambda for constructive interference, and L2 minus L1 equals to m minus half times lambda for destructive interference to occur. Okay, I will explain this in the video later. Okay, constructive interference, destructive interference. Constructive interference occur when the path length are equal, the waves are in phase and undergo constructive interference at P. Okay, for the first diagram. And then the second diagram, when the path length differ by by a wavelength, the waves are in phase and undergo constructive interference at Q. Okay, and then for destructive interference, when the path length differ by half a wavelength, the waves are 180 degree out of phase and undergo constructive interference at out. Okay, so let's watch this video that has been prepared before the lecture by myself. So let's say you have light sources, two light sources, the first one and the second one, and then you have a point you want to see whether the light from the first source and the second source constructively interfere or destructively interfere at point P. So that's the distance from the source 1 to point 1 and from source 2 to point 1 R2. So constructive or destructive interference will occur at point 1. So this is the symbol of path difference. We want to see the path difference between R1 and R2. So R2 minus R1 equals to lambda if constructive interference occur, and then path difference R2 minus R1 equals to m minus half times lambda if the destructive interference to occur. So with the condition for m equals to 0, 1, 2, 3 and so on. M is actually the integer number starting from 0 until infinity. So let's see for the first distance R1, how many lambda need to be there to fit the distance. So first lambda, second lambda, third lambda, fourth lambda, and the last one only half lambda. So it will make a total of 4.5 lambda to reach P1. How about the light coming out from the source 2? First lambda, second lambda, third lambda, fourth lambda, and then last one, fifth lambda. So we need 5 lambda to fit the range from S2 to point 1. So distance 1 equals to 4.5 lambda, distance 2 equals to 5 lambda. So now we want to see the path difference, R2 minus R1. So 5 lambda minus 4.5 lambda equals to half lambda, of course. So half lambda fulfill this equation and condition, the equation and condition for destructive interference. So at point P, destructive interference will occur. So let's move to the second topic, Young's two-slit experiment. So Thomas Young first demonstrated interference in light wave from two sources in 1801, more than 200 years ago. So if you can see on the screen, the light source will pass through two slits and form a series of fringes on the screen, a series of constructive and destructive interference, or bright and dark fringes. So I will just skip several slides to allow you to watch the video that has been prepared before the lecture. Okay, you can read this from the lecture notes. I will explain everything in the video, don't worry about that. Okay. Okay, these are the equation for bright fringe and also for the dark fringe. Okay, let's begin the pre-recorded lecture video that has been made by myself before. So for the young two-slit experiment, of course you need a monochromatic and coherence light source, okay, with a certain lambda. Usually the lambda need to be in nanometer. Okay, these are the slits, the two slits of young experiment. This is the screen. Okay, this is the distance from the slit to the screen, denoted by L. So S1 is the source 1, the slit 1, S2 is the slit 2. Slit 1 and slit 2 acting actually like a source, the first source and the second source. Okay, and then D is the distance between slit 1 and slit 2. The light will pass through the slit and interfere between each other and form a pattern on the screen, a series of dark and bright fringes. So in the middle, constructive interference will occur. Okay, and then a series of bright fringes, and then in between the bright fringes will be dark fringes. Okay, these are the dark fringes, okay, denoted by the brown color. The bright fringes is denoted by the orange color. So let's say at point P, you want to see what kind of fringe is at the point P. So you need to draw a line from the middle of two slits to the point to form a triangle. We need to apply a trigonometry here. Y is actually the distance or the position of the point from the midpoint. That's the theta of the triangle. So from the trigonometry, tan theta equals to y over L. It becomes y equals to L tan theta. So you want to find the series of bright and dark fringes on the screen. Okay. If bright constructive interference occur, if dark, of course, destructive interference will occur. So it's either bright or dark, but how to determine? Okay, you need of course to find the path difference between slit 1 and slit 2 from the slit to the point that we want to measure. So from slit 1 to the point is R1. Okay, from slit 2 to point P, R2. So you can draw another triangle, okay, with the same theta, okay, to find the path difference between R1 and R2. Path difference equals to R2 minus R1. Okay, from trigonometry, you can say that R2 minus R1 equals to d sine theta. Okay, but here, if the path difference equals to m lambda, constructive interference will occur. If the path difference equals to m plus half times lambda, disruptive interference will occur. Okay, and of course, as I mentioned before, the path difference associated with d sine theta. Okay, so R2 minus R1 for constructive interference equals to m lambda. That's the equation. The equation must be accompanied by the condition. The condition is for the m must be equals to 0 for the first fringe, plus minus 1 for the second fringe, plus minus 2 for the third fringe, and then plus minus 3 for the fourth fringe. That's where m is located for the central bright fringe, second fringe, first fringe, second fringe, and so on. Okay, m minus 2. Okay, for disruptive interference, the path difference equals to R2 minus R1 equals to m plus half lambda, with the condition similar to the bright fringe, which is 0 plus minus 1 plus minus 2 plus minus 3 until infinity. So where these m are located? Okay, so for dark interference, for the dark fringe, there are two m equals to 0. Okay, m equals to 0, m is equals to plus 1, m equals to negative 1, m equals to plus 2, m equals to negative 2. So different set of equation have different set of condition. If you want to use equation of bright fringe, you can use the equation of bright fringe with the set of condition for the bright fringe. If you want to use the equation of dark fringe, you need to use the equation of dark fringe together with the condition of for the dark fringe. Okay. So if the angle or theta is very small, okay, it must be very small because the distance between the slit and the screen is a very large compared to the slit distance d, and then the theta will be much smaller than 4 degrees. So we can say that tan theta is approximately to the sine theta. Okay, approximately or almost equal to the sine theta. So from here you can write tan theta equals to y over L. Okay, the equation that has been given before, and then you can compare this equation with the path difference. Okay, the equation of path difference, sine theta from this triangle. Okay, sine theta equals to path difference divided by d. Okay, sine theta equals to opposite divided by the hypotenuse. The opposite is the path difference, hypotenuse is the d. So that you need to compare this tan theta with the sine theta, so that the equation becomes y over L equals to path difference divided by d. So path difference here for the bright fringe is m lambda. So you can apply this equation, y equals to path difference L over d for the bright fringe, and then for the dark fringe. For bright fringe, y equals to m lambda times L divided by d. For dark fringe, y equals to m plus half times lambda times L divided by d, with the same condition that has been given before, m equals to 0, plus minus 1, plus minus 2, plus minus 3 for both bright and dark fringe. Okay, so next we can actually use only one equation to find the bright and the dark fringe. Okay, using this textbook, we need to use two set of equations, but usually we can only use one equation to calculate for both bright and dark fringe. How? We only can use the equation of the bright fringe, but we can control the condition. Okay, the condition, it must start with 0. Okay, and then the following fringe will be half, and then after that it will be 1, after that it will be 1 half, after that it will be 2, after that it will be 2 half. Okay, for integer number 0, 1, 2, 3 and so on, it must be applied for the bright fringe, but for the half number, it will be applied for all dark fringes. Okay, let's say here for the central bright fringe, you need to use m equals to 0. For the first bright fringe, you use m equals to half. For the next bright fringe, you use 1. For the next dark fringe, you use 1 half. For the next bright fringe, you use 2. And then of course the next one, for dark fringe, you need to use 2 half. Okay, it can be continued until infinity. Okay, that's the example for bright fringe. D sine theta equals to 2 lambda. For dark fringe, D sine theta equals to 2 half lambda. Okay, half belongs to dark, the integer number, it belongs to the bright. And then again, we review the path difference. The path difference from the diagram equals to d sine theta m lambda equals to m lambda for the bright fringe, and d sine theta equals to m plus half times lambda for the dark fringe. Okay. Okay, let's continue with the lecture. Okay, this is an example. You can try this question at home, and then you can check your answer with the provided answer here. Okay, next topic, interference in a reflected wave. Okay, an electromagnetic wave undergoes a phase change of 180 degree upon reflection from a medium of higher index of reflection than the one in which it was traveling, analogous to a reflected plug of a reflected pulse on a string. Okay, if you can see here, for reflective index, the N1 is lesser than N2. A light ray traveling in medium 1 undergoes a 180 degree phase change when reflected from medium 2. Okay, similar to the thing that has occurred on a pulse traveling on a string that reflects from a fixed end of the string. If you can see here, this is the incident wave, this is the reflected wave. So the incident and reflected phase will be 180, will have 180 difference, 180 degree difference. And then if N1 is greater than N2, a light ray traveling in medium 1 undergoes no phase change when reflected from medium 2. Okay, the same is true of a pulse reflected from the end of a string that is free to move. Okay, you can see here the incident wave and then the reflected wave have the same phase. Okay, there is no phase change when the wave is reflected from a boundary leading to a medium of lower index of reflection, analogous to a pulse in a string reflecting from a free support. Alright, so diffraction. Next topic, topic 2.2.4. Okay, this is about diffraction. Huygens principle requires that the wave spread out after they pass through slits. Okay, this spreading out of light from its initial line of travel is called diffraction. In general, diffraction occurs when waves pass through small openings around obstacles or by sharp edge. Okay, so this is for single slit diffraction. You may read the notes from the lecture notes. Okay, I will continue and explain in the video that has been prepared before. Okay, for single slit diffraction. So this video is about single slit diffraction. Of course, you need to have a monochromatic and coherent light source with a certain lambda or wavelength, usually in the region of nanometer, and then you have the slit, a single slit, and then you need to have a screen for the pattern to appear. So this is the distance between the slit and the screen. Okay, the width of the slit is denoted by A. So the slit is divided by several portions. So each portion, according to Huygens principle, acts like a source of the light. So we can find the path difference here. The path difference between the portion equals to A divided by 2 sine theta, and then A divided by 2 is actually half of the width of the slit. If the wavelength if the disruptive interference or the dark fringe will occur if half of the slit A divided by 2 equals to half of lambda. Lambda divided by 2 as shown in the equation. If half of the lambda equals to half of the slit, then they will cancel each other. The light will cancel each other, so disruptive interference will occur, provided that m equals to plus minus 1, plus minus 2, plus minus 3, until infinity. So for single slit experiment, single slit diffraction, we need to find the dark fringe first, because we know the condition of the dark fringe is if half of the slit equals to half of the slit, if actually half lambda equals to the path difference provided by the half slit, then disruptive interference will occur. And then how to find the bright fringe? Bright fringe equals to sine theta equals to m lambda divided by A, the same equation with the dark fringe, but we need to use different set of condition. The condition for bright fringe must start with plus minus 1.5 or 1/2, 2/2 and 3/2. So the pattern of the diffraction looks like this. M equals to 0 is actually the broad central bright fringe, and it is flanked by series of dark and bright fringes. The size of each fringe are not the same. It's not similar to the two-slit experiment. For two-slit experiment, the size of the pattern is quite uniform, but for single slit, you will have a very broad central bright fringe flanked by a very narrow bright and dark fringes. So this is the condition for the dark fringe. The dark fringe is denoted by the dark blue color, okay, starting with m equals to 1, m equals to 2, and so on. Okay, and then these are the bright fringes denoted by the light blue color, okay, starting with m equals to 1.5 followed by m equals to 2.5. Okay, that's for single slit diffraction. Is quite different compared to the two-slit diffraction, two-slit Young experiment. The difference is actually on the equation and the condition given. Okay, let's continue with the lecture. So this is the exercise for a single slit experiment. You may try at home. The answer is given. Okay, the last topic, the diffraction grating. The diffracting grating consists of many equal spaced parallel slits. A typical grating contains several thousand lines per centimeter. The intensity of the pattern on the screen is the result of the combined effects of interference and diffraction. Okay, if you can see here, this is the diffraction grating. Diffraction grating meaning that it has, or it consists of many equal spaced parallel slits, meaning that not only one slit, not only two slits, but many slits, perhaps hundreds, thousands, millions of slits. Okay, so usually we use diffraction grating. The usual thing that we can find is actually the compact disc or CD, DVD, optical disc. So electronically, the data will be stored in this diffraction grating. So we use the diffraction grating, another diffraction grating, to interpret the data. Okay, actually the data will be transferred to the disk optically, not electronically. Okay, so or by lights. We store the lights, we interpret the lights. We store the data and then we interpret the data optically or by lights, not by electron or electronics. Okay, a diffraction grating can be used in a 3-beam method to keep the beam on a CD on track. Okay, I think that's all from me. If you need a detailed explanation, I think you may refer to the textbook and then the lecture notes given earlier. Okay, if you have any question, then you can ask me on the Google Classroom, on our Google Classroom. Okay, thank you.